Welcome back to Forge College. Today, we are focusing on building and integrating libraries, a key stop in your journey through our Solidity from Zero track, specifically within the Inheritance and Interfaces course. In our last lesson, Design Patterns for Reusable Contracts, we explored how to design modular components. Now, we look at exactly how you extract the code those components share, package it up, and put it to work. Software engineers have a golden rule called DRY, don't repeat yourself. If you have to write the exact same complex logic twice, you are doing double the work and leaving double the room for mistakes. In smart contract development, we take this rule very seriously. Look at these schematics, a billing contract and a rewards contract. Both perform the exact same percentage math. If we manually copy and paste formulas into both, designs become cluttered. Worse, typing one wrong number bakes a catastrophic error right into your system. We solve this by extracting that common math into a specialized, standalone tool known as a Solidity library. Think of it as a separate toolkit that any of your contracts can borrow from when they need a job done. By removing the duplicated logic, our contract blueprints stay clean. They are much easier to read, and we eliminate the human error that comes from copying and pasting. This diagram shows the specific library we are going to build today. We'll call it PercentMath. Its entire job is to handle percentage calculations safely and accurately. This library is what we call stateless, and it uses pure functions. That means it holds no memory and saves no data to the blockchain. It simply takes the numbers you hand it, runs the math, and hands you the result, just like a pocket calculator. We need this calculator because smart contracts have a well-known quirk. They are terrible at dealing with fractions or decimals. If you try to calculate a standard percentage, rounding errors can literally destroy value. Finance professionals solve this fraction problem using something called basis points. As the circle is sliced, this visual shows how basis points work. Instead of dividing our whole circle into 100 pieces for a standard percentage, we divide it into 10,000 tiny units. 1% equals 100 basis points. By using basis points inside our stateless library, we give our contracts a way to perform predictable, perfectly precise math, where absolutely no decimal dust gets lost in the calculation. Once you write your library, you have two different ways to connect it to your contracts. The first method is called an internal library. When you mark a library's functions as internal, you are giving the Solidity compiler specific instructions. You are telling it to take a literal, physical copy of the tool and permanently embed it inside any contract that asks for it. As the stamp hits the blueprints, you can see it happen right here on the blueprints. The compiler takes the PercentMath logic and directly inlines the contract's internal instructions onto both the billing and rewards blueprints at the moment the design is finalized. The advantage here is total simplicity. There are no extra deployment steps. The contracts just contain everything they need to run right out of the box. The disadvantage is weight. Because we physically copied the code onto every single contract that uses it, our contracts are now heavier. Duplicating those raw computer instructions means it will cost more gas to deploy them to the blockchain. Internal libraries offer a very straightforward, simple setup, but they require you to accept heavier, more expensive individual contracts. That brings us to the second integration method, the external library. Instead of stamping copies everywhere, an external library is deployed to the blockchain exactly one time. It sits there permanently as a standalone, centralized hub. Notice how these wires connect the system. Our billing and rewards contracts are kept small and sleek. Whenever they need to do math, they simply link their wires to the address of that massive central hub and ask it for the answer. This keeps the individual consuming contracts lean and efficient because the logic is entirely centralized in one place, as a signal pulses down the wire. The trade-off is that the contracts must accept an extra processing cost. They essentially send a message down that wire every time they need a calculation. While external libraries require a more complex setup, they are essential for scaling large systems without duplicating massive amounts of code. To turn these blueprints into a working reality, we use a local testing environment called Hardhat. We write an integration script to lay everything out on the factory floor. If we use the external library pattern, we have to follow a strict order of operations. First, we must deploy the PercentMath library entirely on its own, so we can generate its official blockchain address. Once we have that address, we can deploy the billing and rewards contracts. During deployment, the compiler effectively solders the wires together, linking the specific address of the central hub into our new contracts. We can prove this linkage works by running a test call in our script. We ask the billing contract to process a value of 10,000 with a fee of 250 basis points, which is a 2.5% fee. The contract sends those numbers down the wire. The central library does the pure math. It subtracts the fee and safely returns the correct net amount of 9,750 straight back to the billing contract. This architecture gives you a massive advantage for maintenance. If you ever find a bug in your math, you only have to update and redeploy that one central library. Every single contract linked to it instantly benefits from the fix. Moving away from messy, duplicated logic and organizing your code into clean, modular, linked libraries is a clear sign that you are thinking like a professional Web3 developer. To see exactly how these deployment scripts are written and to try running these tests yourself, visit us at forge.college. Forge College was built to help you master these tools. In our next lesson, we'll take these libraries and combine them with advanced design patterns to build even larger modular systems. Thanks for watching, and keep building.